Hi everyone, my name is Yunzhu Li. Thanks for having me here as a workshop on deep learning for simulation. I'm really excited to share some of my recent research on learning compositional dynamics models for physical inference and model-based control. The main focus of this talk is to investigate why we want to learn a simulator from data and how different modeling choices will affect the generalization power and their ability to facilitate downstream tasks in physical inference and model-based control. A little bit about me. I'm currently a fourth-year PhD student at MIT, co-advised by Professor Antonio Taroba and Professor Russ Tedrick. My research interests lie in the intersection between computer vision, machine learning, and robotics. In particular, I'm interested in enabling robots to better perceive and interact with the world via learning-based dynamics modeling and multimodal perception. Before coming to MIT, I obtained my bachelor degree from Peking University. I have also spent time at Stanford AI Lab and NVIDIA Robotics Research Lab. In recent years, we have witnessed a tremendous amount of progress in the field of robotics. In certain areas, robots start to become on par or sometimes surpass human performance. For example, the humanoid robot built by Boston Dynamics has clearly surpassed my personal capability by performing backflipping. Or in the self-driving domain, although we haven't seen a massive deployment of autonomous cars in our daily life, the field has moved a long way over the past few years, and in certain regions, the cars can perceive the environment better than humans by using multiple sensors and can drive themselves more safely and comfortably than many human drivers. But what about robot manipulation? Has the state-of-the-art robot manipulator reached human performance yet? Let us see videos of humans performing various manipulation tasks, including creating an egg, spreading butter on a slice of bread, making dough, and sushi. We can see from the videos, purely from observations of the environment, we can effortlessly perform a tremendous amount of manipulation tasks involving rigid bodies and deformable objects. The ability to handle a wide range of objects and adapt to new tasks goes far beyond the reach of the current robots. In order to bridge the gap between humans and the robots, what are some of the popular methods in robot manipulation? One thread of methods is based on trials and error, using model-free reinforcement learning algorithm. Through an extensive amount of interactions with the environment, the method learns a policy function that maps the observation directly into the actions. These methods are very successful in simulation, and there are many success stories in the game industry like AlphaGo, AlphaStar, OpenAI 5, etc. However, applying these methods in the real world can be troublesome, as they are typically very simple and inefficient and can have a lot of safety issues. This is also not how we humans do tasks. When encountering a new object or a new task, we typically require none or few trials before we can accomplish the task, which is in sharp difference compared with model-free RL that usually requires tens of thousands of interaction trials. Another thread of methods is to build analytical physics models of the environment based on our understanding of physics, like F equals ma, and use model-based optimization to solve the control tasks. This is how classical robotics would do, which have also achieved great success, such as Boston Dynamics. They have spent an extensive amount of effort building accurate models of the robots and using principled optimization methods to derive the control signals, where they can make claims about the system's robustness and optimality. Other success stories including rockets and planes. The problem with writing down the analytical physics model is that it requires full-state information, whereas in the real-world manipulation tasks, like I have showed before, we will have to deal with partial observations. In those cases, full-state estimations is hard and sometimes impossible. Also, this is not how we humans do tasks. When we button our shirt, we may only care about the dynamics in its local neighborhoods. When we push an object from position A to B, we are also not constantly thinking about F equals mu mg. Instead, we have a mental model of the environment. We can predict how the environment is expected to change when we apply a specific action, which refers to as intuitive physics. This predictive ability applies to objects of different materials, including rigid bodies, deformable objects, and fluids, like what you can see from the video. The baby can predict whether the tower will be stable or not after placing the cylinders one on top of another. And this intuitive understanding of physics allows the baby to make a stable tower. When compared with model-free reinforcement learning, using a learning-based intuitive physics model can give us better generalization ability and sample efficiency, which is also easier to specify the goal configuration. When compared with analytical physics model, the routes of learning intuitive physics model can handle cases where the underlying dynamics are uncertain or unknown. Because we learn the model directly from observations, it is also better suited for partially observable scenarios. Let us make the problem more specific. Our goal is to solve the optimization problem by minimizing the objective function defined on the state and action over a time horizon. The optimization problem is subject to two constraints. One is the dynamics constraints, which tell us how the state will evolve when taking the current state and action as inputs. The other one is the policy constraints, which maps the current states to the action signals. The application domain we are considering is primarily on manipulation, where we want a robot to interact with the environment that contains diverse objects with different dynamics. There are three key questions we will have to ask when designing the systems. The first question is, what should be the state representation? The state of the overall systems consists of the state of the robots and the state of the environment. Determining the robot state is easy, as it is designed by humans, and we can add sensors to the robots to obtain an accurate state estimation. The key challenge is how we should represent the environment. The second question is, given the selected state representation, how we should specify the dynamics model, and what model class we should use, and what it implies about the generalization ability of the learned model. Then, given the dynamics model, how we should solve the control tasks is the third question. During the talk, we have to constantly thinking about these three questions, which lays the underlying principle of the modeling decisions. When determining the state representation, we draw insights from our everyday experiences. Specifically, compositionality is common in our daily life. Many ordinary objects contain repetitive subcomponents, ropes and soft robots, granular materials such as coffee beans, Lego blocks, or modeling clay. These objects are known to be very hard for modeling and control using traditional methods. In order to capture the compositionality of the environment and facilitate the generalization power of the systems, we propose to use particles to represent the environment. As you can see from the images, different objects consist of particles, which indicates objects' geometry as well as the interaction within and between the objects. Particle as a representation is very general and flexible, which applies to objects of different materials. Particle-based systems also introduces the desired inductive bias for learning that the particles of the same type have the same dynamics within. To model the dynamics of the particles and their interactions, we use graph neural networks as a modeling class to learn the dynamics, where each particle is a node in the graph, and the interactions between particles are represented as directed edges. For anyone of you who is unfamiliar with graph neural networks, here is a graphical illustration. This graph contains 3 nodes and 4 directed edges. For each directed edge in the graph, we denote the sender as OI and the receiver as OJ. An edge encoder takes the information on both the sender and the receiver and outputs an edge representation denoted as EK. Then, for each node I, we aggregate all the edge representation on edges where node I is the receiver. The aggregation is then combined with the information on node I and fed through a node encoder to derive the node representation. We can then define the loss function between the node or edge representation and the quantity we care to supervise the model. In our case, what we care about is the evolution of the states. Hence, the loss function is the mean squared error between the node representation and the actual state at time t+1. One thing to note is that we exploit the compositional nature of the system, where the node encoder is shared among all nodes and the edge encoder is shared among all edges. Thus, the systems can generate two systems of different sizes or even outside the training distribution, as we will show later in the experiments. We also introduce improved techniques on the base model to improve the modeling power. First, we use multi-step message passing to propagate the information multiple steps over the graph to capture higher order interactions. Second, since constructing a fully connected graph over the entire particle set is inefficient and quickly becomes infeasible when the number of particles increases due to memory limits, we build dynamic graphs over the particle set, where each particle will only connect to nearby particles that are within a certain distance. Since rigid objects are globally coupled, where a small perturbation on one corner of the object will instantly propagate to all particles within the object, we introduce the third augmentation that uses hierarchical graphs for rigid and deformable objects. More specifically, we cluster the particles and assign an additional parenting particle as a root for each cluster. This hierarchical design will enable a more efficient long-distance message passing within the object. Here we summarize the modeling choices we use for objects of different materials. As we discussed before, we use hierarchical modeling for rigid objects. In order to maintain the rigidness of the object, we predict a global motion for the entire object and back-project the movements for each particle. For deformable objects, we use hierarchical modeling, but the motion of each particle is predicted individually to model the deformation of the object. For fluids, we use dynamic graph building where each particle only connects to nearby particles, and similar to the deformable objects, each fluid particle will have its own motion. On the right, we show our model's prediction results, where the inputs to our model are the initial position and velocities of all particles. Our model can predict the long-term future and correctly capture the dynamics of the fluid and the interactions between the fluid and the rigid object. Here we show some more results on our model's dynamics prediction. This example shows two fluids falling down and merge with each other, where the left is the ground truth and the right is our model's prediction. Again, the inputs to our model are the positions and velocities of the particles at the first frame. As you can see from the video, the prediction is very close to the ground truth. Here is another example where we grip a deformable materials using two cuboids, which are to mimic the two fingers of a parallel gripper. In this case, we assume that the gripper is fully actuated, and the inputs to our systems are the initial states of the particles and the subsequent movements of the grippers. Here we show an example of shaking a box of fluids. We assume that the container is fully actuated. Our model accurately predicts the long-term future by taking in the particle state at the first frame and the subsequent actions for controlling the container's movement. As we have discussed before, all nodes share the same node encoder and all edges share the same edge encoder. Thus, our model can generalize to systems with more particles than during training. This example shows that our model can work in an environment containing 2 times more particles than training. The results are not perfect, but it is clear that our model captures the wave of the fluid particles caused by the container's movements. After we have obtained the dynamics model, how can we use for control tasks? In this work, because the learned model is a neural network, which is naturally differentiable, where we can extract the gradients using off-the-shelf packages like PyTorch and TensorFlow. We can then use gradient descent to optimize the action signals and apply model predictive control framework to account for the modeling error. More specifically, here we use the blue dots to represent the initial states of the system. The goal is to achieve the target shown in red. We have an initial guess of the action sequence U and use the learned model to predict the control outcome. We then define a loss function between the predicted outcome and the targets, and then backpropagate the gradients of the loss function with respect to the action sequence. We then iteratively update the action sequence to minimize the distance between the predicted outcome and the targets. The model may not be accurate enough, so we use model predictive control, where we only execute the first action U0. We then obtain a new state X1 from the environments. We then re-optimize the action sequence U using gradient descent to give the model an opportunity to adjust its action sequence to account for the prediction error. Here we show our model's control results. The goal here is to shake the box of fluids, where when the countdown goes to 0, we want the shape of the fluid to match the target state shown on the top left. And here is the control process, and here is the result. Here is another example. When the countdown goes to 0, we want shape to reach the targets shown on the top left. The result is not perfect, but clearly shows that our model's dynamics modeling ability can help the controller minimize the distance between the end state and the target. Here we show the control result in manipulating a deformable form. The decision variable of the control problem here are the position, orientation, and clipping distance of the parallel gripper. After 2 grips, the result roughly matches the target. Here's another example. We have also attempted to deploy our system into the real world by gripping this deformable object to achieve the target shape shown on the top left. Here we show the control process. In order to estimate the particle positions from perception data, we use a depth camera to scan the scene and fuse the point clouds to obtain a mesh of the environment. Since we know how high the table is, we can clip the background and segment the object out, which is shown in the blue on the top left. We then uniformly sample particles inside the surface of the objects to obtain the current particle sets for the model to control on. After 3 grasps, the resulting shape is closer to the target, demonstrating our model's understanding of the dynamics can help guide the controller's actions. Again, the results are not perfect, and there is still a large room for improvements of using a general-purpose robot to manipulate a deformable form into an arbitrary shape. Here we show 2 other examples of manipulating the form into simpler target shapes. Here is a horizontal shape, and here is a tilted shape. And here's the result. We are not the only one who use particles to represent the states. There are concurrent works from friends at Stanford who also use particles to model the dynamics of deformable objects. There are also many follow-up works that scale the system to environments with much more particles and demonstrate stable future predictions of thousands of time steps. Here is a quick recap of what I have just discussed. Again, our goal is to solve the problems shown on the left. And the 3 questions we're asking, we're using particles to represent the environments. We're using graph neural networks as a dynamics model to capture the compositionality of the environments. For the policy search, we're using gradient descents and model predictive controls to derive the control signals. Next, let us dig deeper and investigate the implications of the model class used by the dynamics model. Prior methods such as interaction networks and the project I just described use graph neural networks to capture the compositionality of the systems and model the physical interactions between different constituting components. However, the neural dynamics is highly nonlinear, which makes it hard to adapt to environments of unknown physical parameters and challenging to synthesize control signals. Another direction, rooted from Koopman's theory, there's a function g that maps the original state x to a higher dimensional latent space y, such that the dynamics becomes linear in this latent space. The neural dynamics is linear, which makes it easy to adapt and control. However, it is not designed to handle compositional systems, thus lacks the generalization power. As a result, both directions has its own pros and cons. In a work we published at ICLR-21, we combined the graph neural networks and the Koopman operators theory, taking the best of both worlds and proposed the compositional Koopman operators. Our model can generalize to systems of different configurations and different numbers of components. Its internal linear structure also allows it to quickly adapt to systems of unknown physical parameters and enables efficient control synthesis. Specifically, our model uses a graph neural network to encode the system state X and generates object-centric embeddings G. In the embedding space, the dynamics is linear as shown in the equation. The linear coefficients has 2 parts, which we call the Koopman matrix K and the control matrix L. Considering the embedding is object-centric, it is natural that the Koopman matrix is blockwise, where every block encodes an interactions between 2 objects. Further, the blocks represent the same physical interactions, share the same parameters. Thus, the total amount of parameters only depends on the number of different interactions and does not scale with the number of objects. This provides a good scalability of our method. To make the predictions of the future system states, we also have a graph neural network to decode the object-centric embeddings to the original state space. Leveraging the learned linear dynamics, we can perform system identification and control very efficiently. When adapting to a new system with different physical properties, we just need to solve for the coefficients K and L. Given observation data X, this can be easily done by least square fitting. While performing control with our model, we can reformulate it as an optimization problem with linear constraints, which can be solved efficiently by quadratic programming. Now let me show you some experimental results. The first task is to manipulate a rope by applying forces to the top of the rope. The first row is our model's prediction. Our model only takes the initial state as input and keep predicting future states under a given action sequence. We can see our prediction is very close to the ground truth shown in the second row. Here we demonstrate the control results. The red dots shows the target shape we want the rope to be after certain time steps. We'll use our model to synthesize the control signals and apply them to the ground truth physical simulator to generate the results. Note that in all these test cases, the number of masses, the gravity, and the spring constants are different, where the model has to perform online adaptation in order to effectively control the rope. In the second task, we consider controlling a soft robot composed of boxes with different materials. Some of the boxes have actuators which can perform contracting or expanding. Well, here, the first row shows our model's prediction, and the second row shows the ground truth for simulating the soft robot. Now let us see some control results of swinging the soft robot to a certain shape. The target shape is shown as red grids. We would like to highlight that each test case has different numbers of boxes with different configurations and different stiffness. The same model, without retraining, can quickly adapt to these scenarios and perform efficient control synthesis to achieve the targets. We also have a third task of controlling a soft robot to swim in the fluids. Here we show the simulation results. Here are the control results for the swimming robot. Again, without test time retraining, the same model can quickly adapt to each scenario and perform efficient control synthesis to achieve the targets. To briefly recap, we are considering 3 questions. For the first question, we discussed state representations. We have been using particles and object-centric latent vectors. For the dynamics model, we have used graph neural networks and graph neural networks with linear internal constraints. For policy, we are using gradient descents or conjecture programming to derive the control signals. We are also using model predictive control to compensate for the modeling error. The take-home message here is that exploring the system's inductive bias by modeling the compositionality can help generalizations. It is also essential to investigate different modeling choices and understand their advantages and disadvantages in order to adapt to different scenarios. The final project I would like to discuss is to use intuitive physics model for causal discovery. Causal discovery is at the core of human intelligence. It enables us to reason about the environment and make counterfactual predictions about unseen scenarios. In physical systems, the interactions between different constituting components causally affect the behavior of the physical systems. It is desirable to understand the underlying causal structure and model the functional mechanisms directly from images. For example, when you see the two balls moving around, you could realize that the balls are moving freely over the 2D space, bouncing back and forth between the boundaries, and there may not be any physical relationship between the red and the blue balls. But when you see the second video with the balls starting at the same configuration, you may realize that the two balls may be connected by invisible physical relations, and the hidden confounding variables like relation type and relation parameters causally affect the ball's movements. Humans' ability to recognize the constituting components also applies to more complicated scenarios like these environments with 5 balls. When you look closely, you may realize that there may be a rigid relation between the yellow ball and the pink ball, as they always maintain a fixed distance from each other. The red ball and the pink ball are moving back and forth, and there may be some spring-like relation between them. Our inferences based on the visual observations are exactly right, as you can see from the same video, where we visualize the existence of the edges and the type of the physical relationship. When humans can observe the balls, infer the existence and the type and the parameters of the hidden confounding variables on the edges and predict the future. Similarly, in the closed environment shown on the right, we can find a reduced order representation and then determine the causal relationship between them to reflect the topology of the close. In this work, we aim to discover the causal structure and determine the structural causal model from images, which allows us to predict the future and reason over counterfactuals. This is a particularly challenging task in that we only have images and do not have explicit knowledge of the node and edge variables. Our model, namely Visual Causal Discovery Network, consists of 3 modules for visual perception, structural inference, and dynamics prediction. Specifically, we train the perception module that extracts unsupervised key points from the images to enable node discovery. The inference module then infers the existence of the edges and the exogenous variables that governs interactions between each pair of key points using graph neural network. Conditioned on the inferred graph, the dynamics module learns to predict the future. Here we show the experimental results. We employ the method developed by Kulkarni et al. As our perception module that maps images into a set of key points in an unsupervised way. As shown in the figures, the perception module assigns key points covering the objects and consistently tracks them over time across different frames. An inference module then discovers the edge set of the causal summary graph and outputs a posterior distribution over both discrete and the continuous parameters associated with the directed edges. The figure shows that our model recovers the ground truth graph in the multi-body environment and captures the underlying connectivity structure in the closed environment. The dynamics module predicts the future movements of the key points by conditioning on the current states and the inferred causal graph. Our inference module and dynamics module can also extrapolate to scenarios with different numbers of methods from training. As shown in the figures, the blue bar shows the results when testing our model in environments with the same numbers of balls as training, whereas the orange bars shows the extrapolation results. We can also make counterfactual predictions by intervening on the identified causal summary graph and extrapolate to parameters that are outside the training distribution as shown in the light orange area. As a brief recap, we propose Visual Causal Discovery Network that extracts a structured key point-based representation from videos. It understands the causal relationship between different constituting components and make predictions into the futures. The learning is done end-to-end from images in an unsupervised way, which we hope can facilitate future studies of more generalizable visual reasoning systems. In this talk, I have discussed the 2 downstream applications of the learning-based compositional dynamics models. One is model-based control, where the other is on physical inference. For model-based control, I have discussed how we can use particles or object-centric latent vectors to represent the environment, and use graph neural network to capture the inductive bias of the underlying systems. We've also attempted to incorporate linear constraints in the model to enable more efficient online adaptation and control synthesis. For the actual control algorithms, we have discussed the use of gradient descent, conjunctive programming, and their coupling with model predictive control. For physical inference, we have shown how the compositional intuitive physics model can be used for causal discovery. The lesson I learned is that model is important, and try using the model whenever possible. Going forward, I've been investigating and asking myself the following questions. How can we find a unified representation for various dynamic scenes? And how to use more principled optimization methods for the control problems, where we can say something about the robustness and optimality of the results, and how we may be able to combine multiple sensory modalities for more expressive dynamics modeling, especially between vision and touch. Before ending my talk, I would like to show these videos of humans manipulating diverse objects again. Humans are absolutely amazing, and I hope one day we could be able to close the gap between the robot and human performance. Finally, I would like to thank all my collaborators for the past few years during my PhD. Thank you for listening.